The chi-square test for independence is one of the 3 chi-square tests. The way to identify it is by counting samples and then how those samples are broken into categories. So the chi-square test for goodness of fit is one where we take one sample and then basically we divide into categories in one way. So each thing in our sample is categorized once. The chi-square test for independence is one sample. So a random sample of working adults was taken that collected information about the level of education and work location. So it was a single sample and it collected 2 pieces of data. This is the chi-square test for independence. So for example, if we took a sample and just said, what's your education level? And we didn't pay any attention to where people work, then it would be a goodness of fit test. Or if we paid no attention to their education level, just asked them where they work, that would be a goodness of fit. But the fact that we asked them both and categorized basically each person provided 2 pieces of information makes it a test for independence. The difference between this and homogeneity is homogeneity takes multiple samples. So if, for example, we said we sampled people with no high school diploma, then we sampled people with a high school diploma, then we sampled people with a college diploma, if that were 3 independent samples, it would be homogeneity. But again, we didn't do that. We took one sample. Okay? We're interested in if there's a relationship between the level of education and the work location of an individual. What would be the appropriate test to run? Again, this is the chi-square test for independence. So if we were going to perform this according to kind of our state plan do conclude kind of algorithm for doing these, the state, first thing I would just say is we're doing the chi-square test for independence. I would make sure you state which of the chi-squares you're doing. Now, for us, let me shrink this down so I got a little room to work, the null hypothesis is that work location is independent of education level, maybe we'd say. And our alternative would be work location is not independent of education level. You can word this a number of different ways. You can say there is an association between work location and education, or there isn't. You could, say that education level is independent of work location, or you can switch the variables around. I usually like to assign kind of an explanatory response relationship here. And in my mind, your ability to work at a site or at a location or at home or whatever would be related, maybe caused by the type of job and therefore degree you had, but maybe not. So that's our state. The plan. Well, the plan here is, first thing, again, we want to say what we did somewhere. Then this, because we only took one sample, we don't have to say anything about independent samples. We only took one. The first thing is the total number of people that we asked. So you can see here I've just filled in the table really quickly with some totals, and 418 were the total people in my samples. So 418 less than or equal to 1/10 all workers, obviously true. Check. Now, in a chi-square test, our second condition is that all of our expected counts are greater than or equal to 5. And the way we calculate our expected counts is really like a reallocation of the proportions. We basically would say how many people with no high school diploma worked at site, and then we reallocate that to say, well, how many should have been here? How many people that had a high school diploma worked on at a site, and then reallocate that to here. And the formula is really how many people are in a row. So if I were going to fill in this first cell, I'd say there are 260 people, or excuse me, 206. And how many people are in that column? So times 48, and then divided by the overall total. So I always think it's the row total times the column total divided by the overall total. So for example, this next cell would be 206 times 125 over 418. And we would do this 9 times. We would do every one of these calculations. Thankfully, our calculator can do this for us really quickly. So I'm going to come back to this expected count thing. And let's move on to the do step. And we'll come back. Let's use our calculator. All right, so we're going to put our information in our matrix. So I'm going to press second, and the matrix button on my calculator is right there. You can see I've already used my matrices. Maybe you haven't, but I'm going to go over here to edit. And I have, I'm going to put my information in matrix A. So I have got on our data, we had, go back up here. We had 3 rows and we had 3 columns. And I'm not going to include the totals. I'm just going to include the data. So I'm just going to put it in exactly as it appeared in the original graph or original table. Like that. Now I'm going to get out of here. And I'm going to go to the stat menu and go over to tests, where all of my hypothesis tests are. And I'm going to scroll down to chi-square, not goodness of fit, but chi-square. You see it's saying observed is an A. That is where I put it. Expected, I will not need to calculate. I can just rely on the calculator to do that for me. I'm going to calculate, and here's our chi-square with our degrees of freedom and our p-value. So the do step is basically done for us. Okay, and I want you to notice that really small p-value, the degrees of freedom of 4. Okay, now because we still have not yet finished our expected part, let's go back into our matrices, and you can see matrix B has now been overwritten. I'm going to choose matrix B, hit enter, and there are our expected counts. And you can see that indeed they are all over 5. We should copy this onto our paper if we were actually doing it. All right, so let me just again make a little note here. If I were doing this like on an AP exam or like really doing this, I would copy those expected counts like as a matrix right there. That do step, chi-square statistic, 4 degrees of freedom, was 28.61. P-value was 0.000093. Now where does the 4 degrees of freedom come in here? Let me real quickly explain. We always take the number of rows. So in this case, we had 3 rows, and we subtract 1. We take the number of columns and subtract 1. So we were down to 2 rows, 2 columns, and we multiply. Number of rows minus 1 times number of columns minus 1. All right, our conclude. Of course, we would reject the null because our p-value is so small. And what does that mean in context? It means that we have evidence that work location is not independent of education level. So real quick recap, we knew it was independence because we took one sample and split it with 2 pieces of information per individual. So we knew it was the chi-square test for independence. The null will always be that the 2 variables are independent. The alternative would be that they're not. Our plan step, we had to Of course, to our usual 10% rule, we had to figure out that all the expected counts were greater than 5. We put the information in our matrix and ran the test. Chi-square, 4 degrees of freedom. Number of columns minus 1 times number of rows minus 1. Got the p-value, and as always, our 3-step conclusion. What did we do with the null? Why did we do it? And what does that mean in context? If this video helped you, please like and subscribe for more math help.